Welcome friends. Now let us start the second set of lectures, that's 11 to 20, the problems in the multi-layer machine learning and multi-layer perceptrons especially. So let us start this. All the problems are from this book, that's from me, Machine Learning, and you can get it from YourPedia. So what's true about batch learning versus online learning? Batch learning means all the data we have and we train our neural network all at once, and then online learning means as the data comes it gets trained. So batch learning needs much less storage and is less likely to be trapped in local minimum. No, batch learning shall need more storage because all the data we are having at once, and batch learning needs much less storage, but it's more likely to be trapped in local minimum. C is online learning needs much less storage. Yes, online learning needs much storage, but is more likely to be trapped in local minimum. No, online learning means data is actually coming, the actual data is coming, so local minimum it won't be get trapped. That only happens when all the data you are having, then since entire data is there, then there's local minima are more. So online learning needs much less storage, yes, and is less likely to be trapped in local minimum. That's the correct answer. Online learning needs much less storage, less likely to be trapped in local minimum. Now second question, which can be a sensible convergence criterion for back propagation learning? You shall read this question. You can stop the video, try to solve this problem and then see the answer. The back propagation algorithm is considered to have converged when the Euclidean norm of the gradient vector reaches a sufficiently small gradient threshold. Yes, when the gradient threshold has become small means now the weights are not changing much. The back propagation algorithm is considered to have converged when the Euclidean norm of the gradient vector reaches sufficiently big gradient threshold. No, then it won't converge. The back propagation algorithm is considered to have converged when the absolute rate of change in the average squared error per epoch is sufficiently. Yes, when the error has come small, then it has converged. The back propagation algorithm considered to have converged when the absolute rate of change in the average squared error per epoch is sufficiently big. No. So from here we can learn that even if there is some large question about neural networks and we are not getting it, still what we can do, we can apply our common sense, our logic, and still we can get through those questions. So try to solve those questions, apply your brain even if the question is totally new to you. So here you see, if we apply, it seems that both small, wherever a small word is coming, convergence related with small, first and third are true. First and third are true. That's D, first and third are true. Now, third question, consider the following statements regarding rank deficiency of the Jacobian of a multilayer perceptron. What does this Jacobian matrix does in a multilayer perceptron? Jacobian collects the information. Jacobian is related with the flow of the information in neural networks. Any rank deficiency in the Jacobian causes the back propagation algorithm to obtain only partial information of the possible. Yes, it will block the information flow, that thus you will get only only partial information. Yes, first is correct. Any rank deficiency in the Jacobian causes the back propagation algorithm to obtain full information. No, full information you won't get when rank deficiency is there. Then rank deficiency causes training times to be short. No, if it would have been there, very good, but it doesn't happen. Rank deficiency causes training times to be long because information flow is getting broken. So 1 and 4 are true. Here 1 and 4 are true. Any rank deficiency in the Jacobian causes the backpropagation algorithm to obtain only partial information, and rank deficiency causes training times to be long. That is the answer. Now coming to Hessian matrix. Consider the following regarding Hessian matrix are the higher order matrices, second order matrices of a multilayer perceptron. Hessian is defined as the first derivative of cost function with respect to the weight vector. No, Hessian is second derivative. Hessian is defined as the second derivative of cost function with respect to the weight vector. Then Hessian is defined as the second derivative of weight vector with respect to the cost function. No, cost function with respect to the weight vector. And the inverse of the Hessian provides a basis for pruning insignificant synaptic weights from a multilayer perceptron. Yes, that's also true. So here 2 and 4 are true. D is the answer. 2 and 4 are true. Hessian Hessian is defined as the second order derivative, that's from the definition itself of Hessian matrix, of cost function with respect to the weight vector. And fourth is the inverse of the Hessian provides a basis for pruning insignificant synaptic weights from a multilayer perceptron. Now there's a formula. The correction in weight applied to the synaptic weight connecting neuron I to a neuron J is defined by the delta rule. What is the delta rule? Weight correction is equal to learning rate parameter into local gradient divided by input signal, or which one? So D is the answer. Weight correction is equal to learning rate parameter into local gradient into input signal of neuron J. All these are multiplied for weight correction. Learning rate, of course, learning rate parameter is multiplied, that eta, it comes in front of it, into then local gradient also is multiplied. Weight correction, for weight correction, more local gradient means more weight correction required, and into input signal of the neuron. This has to be multiplied. So this is the answer. Weight correction equal learning rate parameter into local gradient into input signal of neuron J. Now, the model that will be trained with data in one single batch is known as. Now, why I have put this question? Because once you see single batch means batch learning, immediately your mind goes to. But you have to read the question again. The model that will be trained with data in one single batch is known as batch learning or offline learning also. Batch learning is also called offline learning. There's two types of learning, batch learning and online learning. Now, batch learning is also called offline learning. So, C is the correct answer, both A and B. If you immediately take A, then it becomes wrong. So, C is the answer, both A and B, because batch learning is also called offline learning. Now, coming to the seventh question. In model-based learning methods, an iterative process takes place on the machine learning models that are built based on various model parameters. So through iterative process, what are we doing? We are actually correcting the hyperparameters. Hyperparameters is the answer. In model-based learning methods, an iterative process takes place on the ML that are built based on various model parameters called hyperparameters are there. Then which of the following is a widely used and effective machine learning algorithm based on the idea of bagging? Now what is bagging? Bagging is bootstrap aggregating. Bootstrap aggregating has been short named as bagging. There are two methods in that one, bagging and boosting. Now, this random forest is based on the idea of bagging. That is bootstrap aggregating. What we do in that one, we are in random forest or in bagging, what we exactly do, we have an ensemble of a collection of different decision trees. They give their decisions and then we identify decision trees, or there may be other learning methods also. So basically many methods we collect and take decision on that basis. That is the idea of bagging, bootstrap averaging. And one significant feature of bootstrap averaging is that you take one sample and then operate and then put that sample back. So that is the idea of bagging. All the time you have all the data available. So answer is random forest. The random forest algorithm builds an ensemble of decision trees mostly trained with the bagging method. Random forest itself means there's a forest, there are a huge number of trees growing, many methods are there, many classification methods we are using, and on that basis, ensemble of on that basis we are taking the decision. That's the random forest meaning. Now, to find the minimum or the maximum of a function, this is a calculus question, we set the gradient to 0 because the value of the gradient at extrema of a function is always 0, depends on the type of problem, both A and B, none of the above. This is a very simple question, of course. The value of the gradient at extrema of a function is always 0. Whenever there is an extrema of the function, there is a line whose gradient is 0 at the extreme of any function. So the gradient of a multivariable function at a maximum point will be the 0 vector of the function, which is single greatest value that the function can achieve. Now, which of the following is a disadvantage of decision trees? Which of the following is a disadvantage of decision trees? Factor analysis. Decision trees are robust to outliers. That can't be disadvantage. Decision trees are prone to be overfit. Yes, that's the problem with the decision trees. Decision trees take decision on the basis of many questions, but they overfit. That's the most common problem with decision trees. Allowing a decision tree to split to a granular degree makes decision prone to learning every point extremely well to the point of perfect classification, that's overfitting. Decision trees try to ask questions and fit perfectly, and there they get into the problem. Thank you.